And we left off last time talking about the hydrogen atom and talking about the energies of the hydrogen atom. And we mentioned on that last slide last time that the energy of the hydrogen atom only depended on N, not on L, not on M sub L. So since the energy of the hydrogen atom depends only on N, we can work it out if we count up how many L's and how many M sub L's are possible. It turns out there are N squared ways to have an energy of N, or have the energy associated with N in the hydrogen atom. In other words, the hydrogen atom's energy levels are N squared degenerate. Now let's think about what kind of problem I might ask you to do on this. I hope I'm able to figure out a way to do derivations and normalizations and things that, well, normalization wouldn't be too bad. One of my favorite problems that we've done throughout the semester is normalization problems. So what, for example, if I asked you to normalize this particular wave function? It's got the R polynomial that we've talked about, not a particularly complicated one. The R exponential that we've talked about, both are in terms of A0 as a constant, and it's got the sine and the angular portions, theta and phi, that we've talked about in the spherical harmonics. So if I ask you to normalize that, normalization problems look like this. N squared, the normalization constant squared, times the integral over all interesting space of the complex conjugate of the wave function times the wave function is 1. And then we work this mathematics out and solve for n. One of the tricks to this is that in addition to the wave function, we have d tau, which stands for d over all of the space that we're interested in. D tau would be dx times dy times dz if we were working in Cartesian coordinates. You don't have to memorize this, but in place of dx, dy, dz, we could again work this out as a derivation, but d tau is r squared times sine theta dr d theta d phi. So that's an equivalence to dx, dy, dz. And so it appears in addition, or in multiplication, to the wave function squared. So in our case, we have this n squared. And what we've done now is we've broken it out. We've got sine theta, d theta, that's just from the dr portion. We've got d phi, that's from right here. And then we've got the wave function squared. Now we're going to have to move these theta and phi related terms out to where they belong in this integral before we can do the mathematics. But that's really the only algebra that we have to get done before we can get started. And so let's go ahead and take a look at that. Here's what we had on the previous slide. If we move this sign and this sign out to here, we get sine cubed. If we do, since this is the complex conjugate of this, the only thing that's different is negative I and positive I, because complex conjugate means changing all of the i's to negative I. But if we multiply e to the negative I phi times e to the positive I phi, we're adding the exponents. I phi minus I phi is 0, e to the 0 is 1. So the phi term is just d phi. And then we square the radial portion, so we get r squared over a0 squared. And we get, instead of over 2a0 over a0, because again we're adding these exponents. And all this is set equal to 1. And then we just have this mathematics to do to get to solve for n. Now, one of the standard integrals I would give you if you were working this problem is that it's defined as one that pops up very often in mathematics textbooks. It's one that's on the standard integral list on Wikipedia. But the integral from 0 to pi of sine cubed is just 4/3. So we can substitute in 4/3 for this portion. Now the next thing we'll notice is that the integral of d phi is just phi. And substituting in these integration limits for that, 2 pi and 0, we just get 2 pi. So 2 pi times 4n squared over 3 is just 8 pi n squared over 3. We can move out the 1 over a0 squared as well, and so we're left right here. So all we have to do now is take the integral of this exponential. The r4 is here because of the r squared that came from d tau, and the r squared that comes from here. And so that leaves us with just that integration left to do. And what I'll do is I'll pop this equation over to the next slide. Again, please pause and look these things over and try to do any algebra steps that I skip on your own. The whole point of this problem, again, is to solve for n so that we know the normalization constant for this wave function. So here's our equation again. We have a standard integral for that as well. This is one again that I just took from Wikipedia, but from 0 to infinity of x to the n times e to the negative ax is just n factorial over a to the n plus 1, where a has to be greater than 0 and n has to be a positive integer. Now in this case n is 4, so we put 4 factorial on the top. And a is 1 over what we're calling a0, 1 over the Bohr radius. So this becomes just this. 4 factorial is 4 times 3 times 2 times 1. So that's 24. N is 4, so we have 1 over a0 to the 5th. But we have a 1 over a0 squared here as well. But notice this is 1 over a0. So those cancel out to give a0 to the 3rd. There's your 24. This is the terms that we had earlier. Now we have just basically an 8th grade algebra problem in solving for n. And so we've normalized that wave function. We found the normalization constant. Now if we go ahead and examine the wave functions that are shown in the textbook, only the functions that have m sub l equal to 0 don't have imaginary components. This was the same issue for spherical harmonics from rotational spectroscopy. So these can be particularly difficult to plot in 3 dimensions. So just like we did for the spherical harmonics, we can visualize them by writing them as linear combinations of those wave functions that cancel out the imaginary components. And it's interesting, I'm probably covering up the page number here, but I don't know if that page number corresponds to the book you're using. Anyway, key is look up those wave functions just to see them. You don't have to memorize them in your textbook in chapter 9. So the next thing that we'll want to do is take a look at how this theory, because any new theory has to agree with the old theory, where the old theory was right. And so delta E for any transition has to be h nu, where nu is the frequency that causes the transition, so we can rewrite that equation that way. If we substitute in our eigenvalues that we got for the hydrogen atom into that equation, so these are the energies that we got, we end up with exactly what Rydberg had. Numerically, this comes out to, corrected for units, comes out to the Rydberg constant and matches Bohr's theory exactly. And so, I'm covering up the word Rydberg constant right there, so we'll move me here for now. And again, like I said, we get exactly the Rydberg constant. If we want to visualize these orbitals, then the next thing that we need to be able to do is locate nodes, which we started practicing with a little bit in chapters 7 and 8. So let's see. It would be best if we move me back down here for this portion. So because the eigenfunctions of the Schrodinger equation are standing waves, the number of nodes, positions where the value of the wave function is 0, is n minus 1. So we're going to be looking for nodes, and if we know n, we know how many nodes to find, n minus 1. Since there are 3 coordinates, 2 of them angular, theta and phi, and 1 radial, we'll see that wave functions have radial nodes that are spherical in shape, and they have angular nodes that are planar or conical in shape. And so we've had practice finding those angular nodes. We haven't had practice with radial nodes yet because the rotational wave functions didn't depend on R. But we have a little bit of time here to go through some practice on how this would look. So for example, if we wanted to locate the nodes on the 3s orbital, we're going to have to find 2 nodes. And the question is, how would that end up looking? Well, we've got, I'm not going to work this out for you, I want you to work it out on your own, but we've got a situation right here where this function only becomes 0, the exponential part, if r becomes infinite. So that's not helping us find a node. But the polynomial is solvable where we could just pump this into a quadratic formula solving item and find out what values of r over a0 give us 0 for this function. And that will force the wave function to be 0. And it's going to be, since this is a quadratic, it's going to be 2 items, and we'll end up with 2 nodes. So the 3s orbital has 2 nodes, one a ways out from the nucleus, and another a ways out further from the nucleus. And then the function trails off towards 0 as we go further. Locating the nodal surface on a 3p orbital is going to be slightly more complicated, but not too bad. In this case, our quadratic has r equals 0 as a solution and another r. So that r equals 0 is not a node in and of itself. It is a part of the node that we're going to find from sine theta sine phi, and I think this one we worked out already when we were doing the spherical harmonics for rotational spectroscopy. But we'll have another r solution here, or r over a0, and we'll end up with 1 radial node and 1 planar node that takes in the x and z axes. And let's see. Yeah, let's pause there since we're getting near the end of our time. We've only got 15 minutes with this video recorder. And we'll look at a couple more of these on the next slides. But I encourage you to remind yourself, look back through your old notes and justify why these give a xz plane node. This should be in your rotational spectroscopy